Chatelier's principle, or Le Châtelier's principle. I don't really know how it's pronounced. I'm not French. Right? So what does it mean? Well, what it means is that if you have any reaction that is proceeded to completion, or any reaction that's at equilibrium, any disturbances to that reaction, either the products or the reactant concentration, is going to have an effect on the directionality of your reaction. And that just seems so abstract. It's so difficult for people to comprehend. So what we're going to do is we're going to go from abstract to less abstract. So we're going to start off with this abstract definition, and then we're going to give a realistic examples. So I'm going to draw two reactions happening. This is the same reaction, but we're going to illustrate these points with two different terms here. All right, so we have A and B, any reactants, reacting to give us C and D in equilibrium, right? And so what this means is that if you want the reaction to go in the forward direction, let's say for whatever reason we want this reaction to go forward, well, there's two things that we can do, right? One of the things we can do to make this reaction to go forward is to remove some products, right? If I remove C, then we don't have as much C as we used to. We're going to balance this way out, and so what we're going to do is we're going to actually have a shift in equilibrium from that loss of C, and that's going to make the reaction proceed in the forward direction to make up for that loss of C that we've had. And that's one thing. The other thing that I could do is I could add more reactants. If I add more B, I have an excess amount of B, well, we need to balance this thing out. We need to stabilize it, and so what's going to happen is it's going to go in the forward direction, right? That's if I want my reaction to go forward. Let's just say for whatever reason that it's a dangerous reaction and we don't want it to go forward. We want the reaction to go in reverse. I'm just going to say rev for that. In reverse, all right? So what are the two things that we could do? I think you are probably catching on with us at this point at least. We would simply add products and remove reactants. So if we added more C or D, we'd have an excess amount of C and we'd have to balance that out, and so we would move in reverse direction. Or if we were to remove a reactant, say that we removed A from our reaction, well, we need to compensate for that loss of A. We need to make more A to be in equilibrium. The reaction is going to go in reverse. All right, so those are some abstract definitions. Let's give some realistic definitions. And where I live, they do nothing but pick up patients that can't fit into stretchers. Anyways, so we have some generic hydrocarbon compound here. It doesn't have to be CH814. It's something that's a hydrocarbon. It could be even like an alcohol, like ethanol. And that's still, for the purposes of this, combustible and still considered a hydrocarbon, right? So we're going to react a hydrocarbon with what? Oxygen, right? And then we're going to put this in equilibrium, of course, because all reactions are theoretically existing in equilibrium, right? Now, with open systems, things get a little bit different. But anyways, that's beyond the point. What am I going to get out of this? Well, I'm going to get CO2, and I'm going to get water. Now, how do you fight a fire? How do you put out a fire? Well, the most intuitive thing for us from everyday experience is if I don't want, and I'll go ahead and include it as a reactant here, but it's not, I'm just going to draw it right here. We have, that's the fire that we're giving off here. If I don't want this to happen, if I don't want fire to be taking place, what am I going to do? I'm going to stop the reaction from going forward. How do I stop this reaction from going forward? I pour water on my fire to make it go in the reverse direction, and so that it's not producing the fire. Water puts out a fire, right? That's common knowledge to us all. But what's not really so common knowledge is when you blow on a fire, it goes out as well. Now, yes, there's different things with the amount of concentration of oxygen and CO2 in my breath, but a better example of that would be a fire extinguisher. If I have a fire extinguisher and I spray a fire extinguisher on a fire, what's going to happen? It's going to go out. What's in a fire extinguisher? Liquid CO2. So again, if I want to put out a fire, I'm going to put liquid CO2 on it because that's a very dense amount of CO2, and it's going to run in the reverse direction. Now, one of the things that we do a lot of with dealing with forest fires, and this is kind of weird to think about, is sometimes they'll set off a bomb. They'll set off an explosion, right above the fire to suck up all the oxygen to stop it from happening. So if we remove oxygen, guess what? This reaction is going to go in the reverse direction. And we'll show some videos kind of explaining this. But lastly, and I don't recommend doing this, if you wanted to increase the amount of fire for something, what would you pour? You would pour a carbon compound, a hydrocarbon compound, ethanol, octane, something like that. Or you could increase the amount of oxygen doing that, and that's going to make the reaction go forward. That's going to make the fire get bigger, right? So let's look at some videos that really illustrate the point that I'm trying to drive home here. All right, so we have a hydrocarbon combustion reaction happening here. And it's going pretty good. Let's see what happens when this gentleman here sprays liquid CO2 onto the fire. So he's spraying the CO2, and lo and behold, there's so much liquid CO2 that and it's obviously immediately can convert it to a gas, but he's spraying it and it's immediately going out, right? The fire is not able to proceed forward, the reaction stops. Reacting with oxygen to give us a product of fire, water, and CO2. What do you think would happen if we were to remove oxygen? We're going to remove a reactant from our reaction. Let's see what happens. Gets dimmer and then it goes out. Did you see that? We remove a reactant, the reaction goes in reverse. It's not producing fire. I'm about to spray Lysol on a candle, and that's really not a good idea. Lysol contains a lot of other aromatic irritants, some of which are known to be carcinogenic. I do not recommend doing that. If you do, do it in an open system where you have lots of air moving in and out. But nevertheless, let's look at what happens when we add Lysol to a candle that's already currently burning, right? So what are we doing? We're adding reactants. All right, ethanol. This is 58% ethanol, right? The rest of it, other things, but 58% ethanol. That's the main active ingredient in Lysol that we're interested for this reaction. And there it goes. Right there. Lots of fire happening. And then one last example, in case this just still isn't clear to you, would be alcoholic drinks. Now, if you're, 14, 15 years old, I'm going to make the assumption that you know what alcohol is, you know what it tastes like and all that jazz. Let's be realistic here. But there's two different types of drinks, and they're both kind of made in a similar process. One of them is beer over here on the left with lots of bubbles and foam. And then on the right we have whiskey. There's not a lot of bubbles in whiskey. And if you were given a choice of which one you wanted to drink for recreational purposes, I would generally prefer whiskey because it has more alcohol. It gets the job done faster, okay? So this right here, this beer, this has very little amounts of alcohol, very little alcohol by volume. All right, this is whiskey. This has, and hopefully you've ever drinking it, it burns like hell. This has a lot of alcohol. Why does this have so much alcohol, whereas this has so little alcohol by volume? Well, how is this stuff made? How do we ferment things? Well, you probably remember from, I think, General Biology 1, we start off with a 6-carbon compound in glycolysis. We end up with a 3-carbon compound. And in plants, that 3-carbon compound is going to be broken down, releasing us CO2. So it's lost 1 carbon. It's now a 2-carbon compound, and that's going to be converted to ethanol. Okay, anything with an eth means that it is a 2-carbon compound. The nol means that it's an alcohol. This isn't biochemistry, so I'm not going to really stress that. But let's cut this map concept thing out and draw it as if it were an actual reaction. Well, we have a 3-carbon compound that is reacting, and remember, everything's in equilibrium. CO2 and what? Ethanol, which that's drinking alcohols. So that's what's in our drinks. That's what makes us feel dizzy and buzzed at nights. So what we do if we want to have a lot of ethanol produced, we're going to remove CO2 from this reaction mixture. And if we remove a product, what direction is it going to go? If we remove a product, it's going to go in the forward direction, giving us a lot of ethanol, which is what makes whiskey so strong, and beer, there's not so much alcohol in it because there's so much excess CO2. So if we remove CO2, we get more booze from it.